Det var bra.
Egen avdeling for 10 år, eller hva det er, 20 år.
Det var litt kult.
Skjønte ikke når jeg kom inn, så jeg gikk bakens, men det var bra.
Det kom ting ut på kjøpet.
Still people are dropping.
Quick announcement. After the talk, Alexander's side of I will give a detailed overview of all the details of how you actually calculate these rate matrices from the thin torus limit. So that's I would say maybe after the talk take a 15-minute break, everybody, and then those who are interested they can join us here for that.
So it's not at 4.
Well, I would say probably because there might be a slight chance that it will be somewhat longer, I would say maybe it's a good idea to not wait till 4, but just have a 15 to 20 minute break and then start in the same room after the talk. And now we have Gunnar first, who will talk about composite fermion theory for boson-quantum Hall states.
All right. Thank you. So, well, thanks for the invitation to come here, first of all. So I'm very happy to present some of my work here today. And so what I'm going to talk about are systems that we can probably manufacture in cold atomic gases. So as you know, that is something that Nigel Cooper has been very involved with, who has been collaborating with me on this particular project. Okay, so why talk about cold atomic gases? As you can all see, one of the fundamental reasons is that these people really know how to make fantastic pictures. So, okay, but what we really want to know, so we're interested in strongly correlated phases. We believe that cold atoms might provide systems in which we can manufacture these phases in a very detailed way. And so today I will talk about something which we call the rotating lattice, where it's understood that you don't necessarily have to physically rotate the lattice, but you can use some tricks to simulate the effect of rotation, which I will mention shortly after. And so I'll search for strongly correlated phases in these systems, mainly based on numerical methods, and show you what we see there in due course. Okay. So the whole field of cold atomic gases was jump-started with this discovery of Bose-Einstein condensates in '95. So we were able to cool down cold atomic gases to very, very low temperatures in order to condense all atoms, or a very large fraction of atoms, in a cloud of confined gas to their ground state. And so this kind of quantum state is very well defined by condensate, where actually all n atoms in the state are in the same microscopic single wave function. Okay, so now the Bose-Einstein condensate doesn't really have interesting correlations. So from the point of view of many-body physics, this is a pretty boring phase of matter. And so now the question is, how do you engineer interactions that are strong enough in such a system such that you actually go towards strongly correlated states? And that's a fundamental problem because these gases tend to be very dilute, so interactions are weak. And you have to find some means to actually increase interactions to a scale which are comparable to the temperatures which you can reach in the system. And one way to do that is to use optical lattices, where you can find what you create using standing light waves. You create spaces in locations in space where preferred positions for the atoms to sit, and so on each of these lattice sites, atoms will then interact much stronger than they would in a continuous dilute system. Okay. And so the physics on this kind of system can therefore be described roughly, it's very well modeled by a Bose-Hubbard model, where we just have to take into account the probability of tunneling between different sites and the repulsion of two particles on the same side. Okay, so the physics of the Bose-Hubbard model is quite well understood, and so it harbors a very simple transition between a mean field-like superfluid state and a strongly correlated mod insulator state. And so the phase diagram here, which is spanned by interaction strength and chemical potential, you see so-called mod lobes, where the particle density per site locks into integer values. And so, so this is the mod insulator rate. Like exactly one particle on each lattice site, and so on. And in superfluid sites, you have coherent tunneling over large length scales. You have a large number of fluctuations, but a phase that is global to the system. And so this transition has been observed. You can look at interference patterns stemming from such a system. So, basically going from superfluid to models.
Why don't you see Bragg peaks in the mod insulator?
So in the mod insulator you have no phase coherence between different sites. So basically you have to think of this as, so you have a lattice, and so if you have a superfluid, then it's like having a little Bose-Einstein condensate in each of these lattice sites, and they have some coherent phase which is the same all over the system. And so if you release the system, so these phases will evolve in given interference pattern. However, if you have a mod insulator state, the phases become scrambled because the particle numbers.
Why don't you just see density in these experiments?
No, so what you do is you release the lattice potential, you let them expand, and then you see the interference of these particle size. And so when there's no phase coherence, you have no interference. Okay, so this is at least some initial results that show that we can get strongly correlated states in colloidal gases, and that's pretty simple, strongly correlated states. So now another class of strongly correlated states that has been discussed for coatomic gases is namely quantum Hall states, and so these are found in systems that are put into rotation. So the effect of rotation is I guess that's next slide count. But anyway, so the effect of rotation on neutral particles simulates the effect of a magnetic field, homogeneous magnetic field on charged particles. So the Hamiltonian is precisely the same in the case where the confining potential of our finite gas precisely is of the same strength as the centrifugal force that's created by rotation. And so rotation of coatomic gases has been used at relatively low values of the rotation, where they create a certain number of vortices. So the number of vortices is proportional to the rotation frequency, and these will arrange in regular arrays. And so the regime we're interested in is where the vortex density becomes very high. So we look at filling factors, which is the ratio of the vortex density, particle density to vortex density, and we want that to be rather small. to get to a regime where we see quantum Hall states. Now that's difficult experimentally, and so being able to do that in a continuous. But anyway, so we think that below fitting factors of about U=6, these quantum Hall states start to appear, and so these are now bosonic versions of the quantum Hall states that we all work with. So the Laflin state here doesn't occur at a third, but at 1/2, and then at successively larger fitting factors we have a number of fermion states, and then read reside states, which here occur at fitting fractions k/2. Okay, well, so this was written for different ways, I guess. So you all know what the Laflin state looks like. Right. So now in this this concept of rotation kind of was difficult to get to work experimentally. So there's a certain motivation to try and do things otherwise, and so of course you can just now, if you combine both these aspects of an optical lattice and rotation, you might think that since both of these effects direct you towards a more strongly correlated system, it might be a good idea to do both at the same time to get there. So now just physically rotating a lattice is possible, but it's technically very involved. And so this might not be the best way to do that. But there's another proposal which is also out there, which basically consists in saying that, well, if we can engineer tunneling between adjacent sites to have some complex phase, then we can arrange it in a way that whenever particle tunnels all the way around the plaquette, it picks up some constant phase difference, then this is exactly the same effect as that of a homogeneous magnetic field. And so in these papers by Jackson Seller and later versions thereof, schemes have been developed to imprint such phases upon code atoms confined to optical lattices. So you can do things like spatially varying the lattice potential in adjacent sites, kind of moving the potential up and down with a given frequency, and so that gives you a directed tunneling. And due to the time dependence, you get extra phases. Okay, so now let's just assume that we can manufacture such a system, and well, if we have such a system of interacting bosons on the lattice, what kind of phases can we get? Alright, and so the starting point is pretty well known. The single particle spectrum for the particle in the magnetic field on the lattice looks very nice. It's the so-called Hofstadter butterfly, and so as I will explain a bit more in subsequent slides, so there's a nice fractal structure to this figure. And there's a few things you can see immediately. So what do we have here? So first of all, this is the vortex density. The whole figure is symmetric to vortex density 1/2, so that's 1/2 flex quantum per plaquette of the lattice. So this for the case of the square lattice, of course. You might want to consider different cases for different lattices, so there's some degree of freedom as to what the single particle spectrum might be. So as you can always do a gauge transform where you add one flex quantum per plaquette, and so the whole spectrum is symmetric by shifting n phi going to n phi plus 1. So it's exhaustive to consider this range. Well, that had anything to do with strong correlation. I hope it didn't have anything to do with my talk. All right. So how do you look at this figure? So in the limit of very low flex density down here, so these lines are kind of just lambda levels, which come into the origin here. So if you have a very large very low flex density, that means one flex quantum is spread out over many lattices, and so then the lattice is just like a small perturbation, and so we'll give some finite splitting very small finite split into the Landau levels. But as we go to higher flux densities, now the Landau levels split very considerably, so we get substructure and actually new gaps opening inside the Landau. So the number of states inside this lower band all the time remains equal to the number of density of states in the lowest band is the density of flux, just as we have for the lowest band. Okay, and so in this low field limit that has already been studied by Sørensen and Daimler from the Harvard group, and so they found that the last state, for example, is still observed on the lattice. So at least one quantum state, which we all know does occur even in the presence of this lattice.
But the overlap was rather, well, 0.90, but not very large, right? 0.95 maybe, or even lower. The overlap they got for this
Yeah, no,
people
I think-
1/3 on the left.
I think it was beyond
I
0.9.
think
So
0.95.
I'll show you some overlaps which are going to be a bit even lower than 90%. But so I think there's some reasons to believe that since here you, I mean the many-body bases, single-body bases, right, are not nice harmonic functions anymore when you put them in the lattice, so they're already destroyed. So maybe you don't really expect to get the same kind of overlaps that you get in the continuum.
But I think they also did Chernobyl calculations and they found that
What?
they did some Chernobyl number calculations also afterwards to find out if there's problems.
Also show us some this. Okay, so it's now quantum Hall states. How do we understand them? So one very successful recipe, of course, which is one of our favorites, is to use the composite fermion model. And so the idea is simply to describe relations between particles, so these reactions, capture them by this composite particle picture where you attach flux to particles, which then helps to keep them apart and thus minimize the interaction. Okay, and so this is just a little bit different for bosons than the usual case of fermions. So while for fermions, electrons in the fraction quantum Hall effect, you have to attach two flux quanta to get back to a composite fermion. Here we start off with bosonic atoms, and so we only have to attach a single flux quantum to then end up with the composite fermion. And so this described on the level of the wave function by writing such a just factor which describes flux attachment, and the composite fermions are then described by an effective wave function for the particles, and to get a statistical result, usually project this down to the lowest number. And so the flux density that corresponds to this many-body state is simply the flux density of your composite fermion state, plus the flux quanta that you have attached for this just factor, which is equal to m. So I guess I've wrote this factor off to the other side and just turn it around. So. Anyways, so the filling factors now here, instead of the usual p over 2, p plus 1 that we know for composite fermions, ends up being this bosonic series of p over p plus minus 1. And so in continuum, these trial composite fermion states describe interacting bosons well for filling factors 1/2, which we knew. The Laplace state actually is exact for repulsion, but also for the case of 2/3 and quite well still for 3/4. Okay, but now the composite fermion spectrum will not be the spectrum of the continuous particles in the continuum magnetic field, which are Landau levels, but it's going to have these splittings of the bands as described by the Hofstadter butterfly. And so as there are new gaps appearing, for example this one here or this one here, we could expect that there are new incompressible states also associated to these new gaps. And so there can exist incompressible states with no counterpart in the continuum. And so now the question is, where do these states occur? So what are the flux densities or particle densities before we get any new states? So to do that, to to find out, we have to just simply count states in this Hofstadter spectrum. And so that was very nicely presented in this original paper by Hofstadter, which is his only paper. I think he's probably the only physicist that has a single paper with over 700 citations. And has never written any other paper afterwards. So, interesting. So, okay, so what's the structure then? So we have, I've cut it in half. So the butterfly is to be seen as these 4 gaps of the main cell. So that will continue on the other side of that butterfly. And so this butterfly is the structure that then recursively appears in all the subcells. So the subcells, for example, this is one subcell here. Highlight that in the next slide. Okay, so Hofstadter has turned the spectrum around and he calls them the left, central, and right cells. So anyway, so we have subcell L1, L2, L3, and then we come to small to the C. And so this is the central subcell number 1. And so if you imagine that you pull this thing into a rectangle, just like the unit cell, to do similarity transformation that way, then it will look precisely like the unit cell. And so we can describe mathematically what the operation corresponds to. So actually one of the properties of the spectrum is when you're at a fractional flux density of P over Q, they're precisely Q bands. And so the number of states in each of those Q bands is the same. And so to the filling or number of states below some band, all you need to know is how many bands are below that gap, and how many bands are above that gap. And so now subcells, to count the number of bands, so you introduce this local variable of beta prime, which would be the density that you map the spectrum to if you drag out the cell such that it overlays the unit cell, the spectrum radius down. And so this is simply the inverse, the integer part of the inverse of the flux density, and up to some offset n, which gives you the number of the subcell. So now, anyways, the denominator of the, anyways, we just have to calculate the denominators of these variables to get the number of cells. Number of bands. At least different points. All right. So, for example, what I want to calculate is let's take this flux density and say, well, we want to find out how many states on this little band down here, such that we can describe the filling factor. So the total number of bands follows from the flux density that we're at. So now we have to know what's the local variable in the subcell. So we use this equation here in the inverse. And so the numerator of this beta becomes the denominator of this beta prime. And so therefore this is simple. So the flux density is P over Q. Beta equals the vortex length. Oh, sorry, I think here I've taken all the bands down. So this P was all the bands in the subcell. So basically that was just proving that this is really just like the splitting of the lowest number. So the number of states in that whole lowest band is equal to the flux, number of flux. Okay. Now the next step is to cut this apart and just take the next subcell and count the bands in that little piece there. So we do this transformation once more. So it's going to be beta 2 prime, which is the local variable in this little subcell as a function of the local variable in this subcell, somewhat bigger subcell here. And so again, the denominator ends up being the numerator of the previous one. And so now here we get the filling, which is n equals to 1 minus larger n beta, where n was the index of that subcell. So the crucial point here is that n, the particle density, depends in some linear, depends as some linear function of the original flux density. And so this is something about that, since this whole structure is defined recursively, you can prove by induction that must thus be true for all gaps. So whenever you stay within some gap and you fit on that one, you move around with left and right, the number of particles that you need to fill all states up to that gap is going to depend linearly on phi. Okay, and so now linear functions are pretty nice because once you know 2 points on the line, you can construct the whole curve. So you can deduce at what states in the space of particle density and flux density you will have gaps. So this is taking the gaps of the Hofstadter spectrum and then do a composite fermion transformation so that tilts the axis n phi versus n a little bit. Anyways, and so you see wherever there's a light line here, that's a ratio of n and phi, where you would expect the gaps many times in the composite fermion picture. So everything that's coming out of here, out of the origin, those are just continuum quantum Hall states. So the biggest line here, that's nu equals 1/2. The next one there, that's nu equals 2/3. Well, this whole series converging against nu equals 1, which would be the diagonal. Actually, this black here is not. It's just present because I did only include fractions with denominators up to 50 in this plot. So you could fill, there would be increasing density of lines close to the. Okay, but so crucially, we have new lines coming out of, for example, n phi equals 1/2 here, where one could also expect a gap. So there's a bunch of lines here. And so if the composite fermion picture is appropriate to describe the system, we should have some correlated Manibali states there, some gap Manibali states on these lines too. Okay. So now, do these new phases describe the actual ground states of the system? So we'll check that numerically using exact diagonalization. And so we've just used the square lattice periodic boundary conditions, so put in the torus, and we use Langev's methods in the standard way to get the low-lying spectrum. And so unfortunately here, the Hilbert spaces grow much more unfavorably than they do in the lowest number level, because you do simulation kind of on these discrete set of states, rather than on a countable subset of the lowest number level states. So we take all the rest of the spectrum along as well, everything that's above the lowest number. So we expect to be rather limited in particle size, but also due to the lattice, so we have some extra geometrical parameters like the aspect ratio and so on. So finite size is probably going to be a bit worse than in the continuum as well. Anyways, so once we have these exact states, how do we know that they are composite fermion states? And so it would be good to have the analog of this composite fermion wave function on the lattice, so we can check explicitly and look at the open. Okay, so that's the well-known composite fermion wave function in the continuum. And so we exploit the fact here that the slated determinant of the lowest number of wave functions is the Vandermonde determinant, so it's the slated determinant of all the orbitals in the lowest number. And so we construct something analogous on the lattice, where we just take the numerical spectrum of all the states in the spectrum, we select those which are in the lowest number level, put them in a slated determinant, that gives us a Jastrow factor. And so what's nice about this is you can, in your lattice, define some twisted boundary conditions for translations around two orbits of the torus, and so get a whole class of wave functions here. Or if you globally fix these twisted boundary conditions to be to give you zero phase, then you can still have some phase phi x, phi y in this Jastrow factor, and you just put the opposite phase factor into this composite fermion. This will allow us to get multiplets of wave functions wherever we expect topological degeneracies to occur in the torus. story, and we don't really know how to do lowest lambda level projection. So on the other hand, since we are dealing with hardcore bosons, maybe lambda level projection is actually not appropriate in the lattice. So so let's just go with this one and see what the results are.
So, recombinant was taken, was not taken.
Oh, okay. So, well, I mean, you might expect that by scattering of these particles, you have components of higher excited states in your wave function as well. Okay, so for nucleus 1/2, using this numerically generated Laughman state, you can reproduce exactly the analytic Laughman state, so which has a very high overlap with the ground state up to vertex density about 0.4, and so those numbers have been generated previously from the Laughman wave function. So I don't replicate that plot, but point by point, you get the same overlaps up to maybe 0.05% deviations. So now, what's interesting here is we can look at different constant fermion states as well. So we can fill multiple lambda levels of constant fermion lambda levels and get this 2/3 state. So now here in this subspace we have 3 states because denominator 3, so there's a threefold topological degeneracy. And by varying these toroidal fluxes, phi x, phi y, we can span this multiplied of 3 independent states and get a total overlap of 1.8, so that's really 3 times 1.8. And so this drops at a flux density of about 0.2 or so. Well, somewhat irregular behavior of quantum system sense. But if you go back to the single particle spectrum, you don't really expect it to be valid all the way down because there's additional structure appearing in those shadow bands. And so you can also go to cases which are mu greater than 1, where this constant Fermion wave function still does a fairly decent job of gives you overlaps of around 0.6 in the case of 3/2, and something similar for nucleus 2. So there's an interesting phenomenon actually of this curve going up. That's due to the fact that the Hilbert space is the smallest for nucleus 1/2 and phi equals 1/2. And so, well, if you go to smaller Hilbert spaces, your trial wave function tends to become more accurate. So I think the interesting bit is actually the left paragraph. So now, of course, in the continuum we know that the composite fermion states are likely not realized, rather to have really precise states with those spin factors. It will be interesting to look at those in due course to study their competition on the lattice. Who knows, maybe the lattice actually may influence the competition between those different phases. Okay, but so now we really want to mainly look at these new states and see if this line that was predicted by composite fermion theory in the lattice actually corresponds to the series of correlated Mendel states. And so this line cuts through a number of these other composite fermion lines, and so we decided to only look at things which are at particle densities below n equals 1 sig, so that we are on this low part of the curve. And so for number of theoretical reasons, 1/7 and 1/9 are the most suitable cases to be looked at. So mainly you want to look for systems which have which give you a sequence of numbers which you can only simulate it on the finite lattice and which don't have aliasing with other things. So these two work out. So the geometries are in this case 2 by 7, 3 by 7, and so on. And so you start off with an overlap for 2 particles, which is on 0.4, and that actually increases to about 0.74 for 3 particles, and then kind of oscillates. So this intermediate case here is, this case of 4 particles is quite interesting, because the ground state there has no overlap, it's actually at a different momentum. So this, in this case here, you get a charge density wave state, which is actually the ground state, which is the particles delocalized around the short direction of the torus. So there's this completing phase, which is actually also known from the continuum. And so what we think is that since if you go to here a bigger system with a more homogeneous aspect ratio, the composite fermion state again seems to give at least some decent description for the ground state. We think that the composite fermion state likely wins out over this charge density. And for 9 particles, we have a similar situation again for 4 particles. You have this effect that the ground state is at a different momentum.
So I think you mentioned it, but I think I missed it. You were saying there's a new series of states that don't have a continuum analog.
Yes.
These are the ones.
These are the ones, yeah. So these are 2 states on this line.
See,
On
the
this
reason
red
why
line.
I'm a bit uncomfortable with that is the Hofstadter problem is nothing else but a Landau level with the periodic potential. So I would expect. I guess I don't really understand why they don't have a continuum analog. What do you mean by that? I think you mentioned it, but I didn't.
Okay, so basically, so the nu equals 1/2 state tells you that you take bosons, you attach one flex quantum, and then you fill the lowest Landau level. So the lowest Landau level is all the states below this big gap. And fine, you can do that. And it works up to flux around 0.4. And then it starts to, this construction stops to work. Now if we look at this spectrum, at the Hofstadter spectrum, we see that this gap here is new. Right? Wasn't there before, without the absence of lattice that was moved.
Well, but
The
this
lowest Landau level would have just been completely generic. So, and now we can potentially construct a many-body state where the composite fermions fill only this lower band up to this subgap in the subcell. And so I think that has no chance of occurring in the continuum.
is that. Okay, I guess that's something that White has no chance of doing in the continuum. But
So,
we can talk about it. I mean, to me, the Hofstadter spectrum doesn't really differentiate between a Landau level with a periodic structure. So if you fill whatever number of bands you've got, it's like filling.
so you mean if you have a Landau level with a period?
If I have a Landau level with a periodic potential, I can generate a Hofstadter spectrum. Right? It's not Hofstadter spectrum does not have anything that a Landau level doesn't have.
Right, well, so
besides
the
the
analogous statement is if you add a periodic potential to the system, you get new states. So you don't necessarily have to work in this Hubbard, Bose-Hubbard limit, right, where you consider hopping between different sites. You can also look at a continuum model plus the perturbation of the periodic potential. So this line here has an equation which is flux density equals to 1/2 times 1 minus m. And so in contrast to the continuum equal states, so the filling factor is not well defined. Right? If you take n divided by m5, that depends on n. Right? So I mean, you can continuously tune through all filling factors that you please to want to have. At least as long as you stay in this low part. Okay. So again, these are the numbers for overlaps, and so now, as we pointed out earlier, so in the continuum we're used to composite fermion wave functions which have an extremely good overlap with the exact states. So now, first of all, we did include a Landau projection there, which we omitted here. So whenever we fill bands, then well, we don't exactly know if we have done right by omitting this projection. So potentially, at least, if you do it, you might increase those numbers. So still, well, 0.45 in a Hilbert space of 1.2 million, 0.3 in a Hilbert space of 5 million states are not quite accidental numbers. So definitely not in agreement.
No problem. But when you do this kind of things, don't you try to extrapolate to the thermodynamic or then put together an answer? And if
For the
you have
overlaps.
something which depends so much on the size of the system that you are choosing, which is going from 0 to 0.8, I mean, how can one be comfortable with the thermodynamic to know it's one solution?
Well, I mean, all we say is that the constant fermion model is helpful in describing these phases. We don't say that these states are necessarily precisely constant fermion states. So, I mean, there's some other things. For example, you know what the ground state degeneracy is supposed to be, right? So in the case of the 2/3 state, for example, you get 3 states. Here, for this line of the fermion model predicts the degeneracy of 1. And so there's a single state in the spectrum which has some gap, which is larger than the typical level spacing at adjacent values of the flux, for example. Well, so now it comes to the fermion state, there are no free parameters. And so there's some other more qualitative features that we'll discuss next. So you can calculate Chern numbers. So the Chern number predicted by the constant fermion theory here is 2. And so I'll show you that we calculated those and those come out right. And so even though the overlaps are not that great, so you have at least a phase where 2 topological quantum numbers, the ground state degeneracy and the Chern number, come out according to the predictions of your model.
Question similar to Andrei's question. So these states with 1/7, 1/9, and in principle I can obtain them if I take bosons with long range interactions without any lattice. Is it correct?
Oh, but this is not.
Or is this a different state?
This is not. Oh, so these are not. Sorry, I should have. This is the particle density one. But we have a flux density which is given by this equation. So n phi for the vortex
It's just not
1/2 times 1/9.
Okay, so it's not just Filling fraction.
It's not a filling fraction. So these are not mu equals 1/7.
So if I take particles with long range interaction, I can in principle obtain the states.
I don't think so. You need the
You really
lattice.
need this spectrum.
You need the lattice. So as I explained, this curve results from this sub gap which I showed you, which I pointed out in the Hurtado spectrum. And so that's just, we've chosen that one because it's the biggest gap except from the main gap, which is
This spectrum has some fine structure. How this fine structure appears in your theory?
the spectrum.
Yes.
Yeah, so I mean, you can actually see it on this graph, right? I mean, or maybe you can't see it. No. So there's so of n phi equals 1/2. So there's this curve coming out. There's one here. There's going to be there's a whole fan of these curves which become weaker and weaker and weaker, coming corresponding to smaller and smaller gaps in the spectrum. And so they're just difficult to see, but they are there. And so actually there's so this whole spectrum is recursive. So whenever you take some unit of the Hofstadter spectrum that corresponds to a subcell, you can draw the same kind of diagram, the same set of lines in that subcell. So for example, so between u equals 1/3 and u equals 1/2, now I don't know exactly which, something like this, you would have the same, exactly the same set of lines that are shown here, would be in that segment, because it's a recursive structure. So this is just, if you wish, this is something that's derived from something that has from some geometrical structure which is fractal, so it has to be fractal.
But your composite fermions will have this structure.
Yes. So, yeah, as you point out, these numbers are encouraging, right? So it definitely shows us that the composite fermion theory has something to do with our ground state. It's somewhat non-trivial to get this overlap. If you just made a random guess, this wouldn't work. So there are some other things. So this ground state is definitely not condensed, right? So we started from something where we have a Bose-Einstein condensate. Right? So, and so there you can look at things like the eigenvalues of the density matrix. So the density matrix will have exactly one eigenvalue that is large if you have a condensed state. So here in the case of these correlated many-body states, so you get typically for n particles n eigenvalues of order 1, or maybe 2 n eigenvalues of order 1/2, things like that. Things that give you stable scaling of the absolute value of the eigenvalues of the density matrix of the system size, so they don't grow with them. Okay. So one thing we might want to calculate is the Chern number, and there's a nice graphical way of doing that calculation, which was described by Hatzel in this paper there. So what's the Chern number? So the Chern number is defined for any set of quantum numbers that are defined in a toric boundary. And so define over those quantum numbers on a torically closed surface, like the ground zone, for example. Then the result of this flux, it's just a field. The field tensor gives you an integer quantized number. And so A nu, for example, can be the Berry connection in a subspace of the ground state subspace. And so for Hall states, the Chern number is related to the Hall voltage, and so we know that it has to be quantized. And so now, if you just wanted to calculate this integral numerically and do this derivatives and all the rest of it, then this is really a horrible task. You would have to discretize a two-dimensional surface and calculate derivatives. So pretty hopeless to do anything there, especially since calculating each point requires you to do an exact diagonalization, a separate exact diagonalization. So anyways, so this integral here is taken over a closed surface. So if we were to have a continuous function without any singularities that we integrate, we know that the result has to be 0 by Stokes theorem. And so we can trace the contributions to the integral to places wherever the vector potential becomes singular. And so now when we have such singular points, then we can always make a gauge transformation that leaves the field strength invariant, but removes the singularities from the gauge. So we just move them somewhere else. And so basically now, if we find such a gauge transformation that moves our singularities, now we can just count them and find all the contributions to the integral. Okay, so how to construct such a gauge transformation? So come back here. So the gauge doesn't only transform the vector potential; it also transforms the wave function. So given some gauge, right, after applying the gauge transform, we get this extra e to the I chi, p by chi was the gauge that we get. And so now, as we argued that we can, all the contributions can be removed by the gauge, so actually only the gauge will contribute to the integral, so we only need to integrate over that gauge after we remove our singularities. And alright, so now to construct that gauge, we just take two different gauges chosen by two different conventions for finding our wave functions, and then we find the gauge as the relative phase between those two different choices. Well, the wave functions in those two different choices of gauge. Sorry, that's a bit. Anyways, so now, alright, so So we take, for that to work, so we take two reference states. So we take a given choice of the twisted boundary conditions. We calculate the ground state that defines psi and phi. And then we take a different choice of your very boundary conditions that gives you phi prime. And now basically you search the transformation, the gauge transformation that would bring one state into the other. So that defines a gauge. And now you just go ahead and plot this gauge as a function of your twisted boundary conditions, and you see that this is a vector field which in most places is just regular, and then there are a few single vertices which you can just see. And so you say, well, that's a vertex, and that's a vertex. So trend numbers 2.
How does this picture depend on the number of sides you take?
Oh, I can show you the graphs, but so the position of these vortices, they kind of wander around. Depends on what kind of reference states you choose. Right? So the number is an integer which remains constant.
And you can use any reference state you like as long as they're not exactly the same as each other.
Unless they're orthogonal, yes. They're not orthogonal. Yeah.
Not orthogonal, and they're not identical.
They're not identical. So yeah, they're identical.
If they become orthogonal, do the two overlap or something?
Now, if they become exactly orthogonal, then these vortices tend to move away very far, and if they become more similar, then they move closer.
So you extracted from your Hexagonal animation.
Yes. Yeah. So this
You always
is,
see two vertices.
So yeah. So where does this come from? So the vectors here, right? This reference vector and that reference vector come from out of exact anglization, and then we do it in exact anglization for all these points in your space of boundary conditions. So this is, I don't know, 20 times 20 exact anglizations or so. And it's and yeah, you just plot this vector.
But supposedly to have more than two vortices, you need some of the vorticity has to be 2.
Okay,
You could have plus or minus vortices
Okay,
everywhere.
so
Right?
yeah, there are two more vortices. There's one here, and there's another one there.
Yeah.
And you didn't count those,
Yeah.
right? So basically, what did you do?
Right.
So this integral is constant, right? So if you do gauge transform, you still get the same thing. So there were the two original vortices, and you move them, right? And then they're somewhere else. And so you see, actually, that's right, you see the ones that you had before, and then you see the ones that, so these two vortices move to these two new positions. And actually there's this field indicated by these diamond signs. That's giving you the scale of one of these two scalar products. So basically, so if you're in this gauge, then you have to multiply with that factor to get the wave function. If you're in the other gauge, you need to multiply with that factor. So now you don't use a gauge transformation that brings you from that vector to that vector. So you go first to this state by applying that gauge, and then you go from that state to that state by applying the inverse of that gauge. So whenever this thing becomes 0, this gauge is not actually well defined. And so those are the points where this thing becomes single. So it's kind of a bit sloppy to write this as a phase, because it also has an absolute value to it. And so you just then count the singular points where one of these factors becomes 0. And that's what you can see here, is the diamond symbols actually vanish there. Anyways, technical detail. So let me summarize anyway. So I think Ashiko and bosonic atoms are quite an interesting system to look at if you want to find new strongly correlated phases. And so I think we've just started to really explore this world of lattices, systems of lattices. So you can play with lots of parameters, and you can take different lattices. And we certainly, even in this case, haven't explored all the states. We looked at the re-resized series. That's still present in the lattice. So potentially, at least, this might be a system where we can realistically hope to see these phases, maybe even non-abelian states. All of what I've shown you today, of course, was abelian. All right. So the constant Fermi construction was quite successful in describing these states. Of course, not all of the potential candidates that we have constructed will be confirming states. They are competing phases, one of which we've seen to appear as the points which we looked at, which was a charge density wave. In general, there will be many condensed phases lurking, so these are bosons selected and dense. So you have to look on a case-by-case basis whether these predictions are true. But nonetheless, we find emergent evidence for uncondensed phases, which are well described by the Fermi construction, both qualitatively and quantitatively to some extent. Right, and so there's still a lot to play with. So in case you're interested, please join the game.
What is going to survive if the density is not exactly homogeneous in the system, in the atomic lattices?
Yeah, so that's a concern. So we've tried to just look at the
homogeneous
cases.
Right.
So, I mean, the simplest picture that you could imagine is if you have a spatially varying potential that the density likes to lock into, incompressible states, and so you have this kind of wedding cake structure where you have a higher density quantum Hall state in the center of the trap, and as you go up, there's other things and other fraction quantum Hall states, or maybe for instance towards the edge or something. Yes.
So have people studied similar things for just interacting electrons in a periodic potential?
So there's a paper by Cole and Reed, 96, where they discuss complete Fermion construction on the lattice. So they write down
Has that been?
So there was no numerical test of that theory prior to this. And so actually, I believe bosons is a bit simpler to look at than fermions. So if you go to fermions, you attach two flux. So in order to typically get lower particle densities, and so you have to simulate bigger systems to get the same number of particles. And so it's numerically a bit more hairy just because the Hilbert space here is growing so fast. It's simply more difficult to look at.
I suppose you studied part of this short range interactions.
Yeah, so this was hardcore interactions.
So how interactions are modified?
Oh, yeah, so I think the Harvard group has looked at dipole interactions, and they found that if they do that for the Laughton states, they can stabilize the Laughton states up to higher reflex density and also see μ+1,4.
So, and these non-evident states, where would you expect to see them along the diagonals?
Yeah, so the diagonal would be the Pfaffian state. μ+1. Well, I don't know. I haven't looked at the trials. But to me, at least in parts of the diagram, that looks actually condensed. So it doesn't look strongly correlated at all.
Are there any other states, non-evident states?
Yeah, so the most evident, μ+3 halves, μ+2, those are supposed to be weak reside states.
I mean, the ones specific to the lattice.
Oh, the specific to the lattice. Yeah, so these ones are reliefs, so they are just constant Fermion states, so they should have the same universal properties as the constant Fermion states.
Do you have any comment on the temperature scale that you need in order to have these states?
Oh yeah. So the gaps are about 1/20th of the interactions. So that's about a quarter of the gap of the Laughton state.
What would you measure?
What would you measure? Yeah.
These are not, they're not charged.
They're not charged, yeah, but you can, so you will want to measure, for example, correlation functions. So you just take instantaneous snapshots of the particle positions in the lattice, if you manage to do so, and then see if they match up your predictions for correlations in these phases.
Even quantized densities.
Quantized density.
Yeah, the gap, the incompressibility.
It's kind of zero for all of that density, yeah.
Zero. But the best part of the question is how to realize it, because if I remember,
Yes.
what is it, in their paper, they will apply tunneling in that direction, T1 to T2, then you apply a quadrupolar potential, then from T2 to T3, then you apply tunneling in the y direction from T3 to T4, and again a quadrupolar potential. Then how do you get a handle on that?
There was some experiment recently where they realized there's some.
Well, now Jan Spielman has a way to generate a mist. He has a way,
Yes,
site
yeah.
with him,
Yeah.
to generate a vector potential. But it's using Roman. It's not like they said, it's a different way.
That's interesting. Yeah, so anyways, I mean, we've just taken this as, you know, as well.
So
What
how
can you
do
do
you-
with the system once you're able to realize it? So it's true that the new proposal is to how to do it. I think Bill Phillips could
Yes, exactly. Jan Spielman now he has a way.
has
Yes.
different concepts.
Exactly.
How do you measure conductivity, the conductivity chart?
Yeah, well, conductivity is of course always a bit difficult to measure in finite systems, confined systems. But yeah, maybe you can.
I mean, do you have any idea about, you can have block oscillations if you just have a periodic lattice, what happens if you instead you keep the lattice with some additional potential? I mean, how a particle will explode towards the spectrum.
How will particles explode the spectrum? Yeah, so
I mean,
it's a good question. So I mean, just naive answer is that, well, if you have these quantum Hall states, most probably the carriers will be some quasi-particles of that state, and so they
What about thermal conductivity?
thermal conductivity. Well, refer to my last point, if you're interested. Join the field, and please find out.
Well, at least for graphite, we know that when they measure this Nernst effect, the peaks coincide pretty well with the quantum Hall plateaus. So it should be a way.
It wasn't the
It is a
joke.
signature.
I mean, also in quantum Hall
Yes,
sector,
yes.
I know that thermal.
They know it for bismuth and they know it for graphite. The Princeton
Yeah.
has been measuring it. And they see Nernst peaks every
Moller
time
and
where you have a quantum
have
Hall
done that a
plateau.
long time ago in the
Yes.
90s
Yes, yes.
on quantum Hall
Fully.
systems. So, thermal signal might be something that you could see.
Okay, so then we would have to look into the system and look how that propagates through well, the system. I think actually probably for now people have hard time enough to get them code enough to actually see this. It's probably not so much of a
If it's very cold,
Further questions? If not, let let's resume in like 15, 20 minutes for those who want to join the
we also have.
So, in full detail,
This is
hello, nice to see you.